All right.
Hello and welcome to another session of our HSC's fall seminar. Today, it's my pleasure to introduce our speaker. Adrian Sampson is an assistant professor at Cornell, focusing on quite a lot of our favorite relevant topics, such as architecture, program languages, compilers, accelerators, and open source hardware. Of course, it's our favorite. He completed his PhD at the University of Washington and has been quite an active member in our church community, and especially helping keeping our social media world alive in our church community has been nice. So with that, I'll be really excited to hear what he has to tell us about today.
Awesome. Thanks so much, Scott. Yes, it's true. Tweeting is the most important part of my job. But today I'm going to do something else. I'm going to actually talk about research. So I want to tell you about a couple of projects that are going in our lab that are around the theme of making the high-level design of accelerators more predictable. So I'm going to be telling you a little bit more about what I mean by predictable pretty soon here. But I want to just first sort of like map out like what we're talking about here, kind of like in the context of like open source hardware and the tools and the very cool looking talks that I see y'all have had in this series in the past. That is like, you can sort of imagine like this entire ecosystem of tools like surrounding hardware design that are super important to getting any hardware design done, that sort of like start at the RTL level. I know that there's like stuff going on here at Santa Cruz, and I couldn't resist like mentioning the cool stuff like going on with like representing programs at kind of an RTL, HTL level of abstraction, or simulating that stuff. And that is all super important, but it's not what I'm talking about today. Instead, what I want to talk about is above this. That is how to generate hardware designs, that is like RTL designs, from high-level programs. And what that means to most people is HLS. That is, it means the wonderful tools you're familiar with, like Vivado HLS or Intel's HLS tools or a few others that take C or C++ programs or maybe OpenCL or something like that and compile them to RTL. And I think that a lot of people have a pretty strained relationship with HLS. I think it's for good reason. There's a lot of reasons that HLS is sort of like, has accomplished a lot, but nonetheless remains a sort of frustrating way to design hardware. And that's what I'm going to be complaining about for the first part of this talk. But moreover, HLS tools are, well, first of all, they're usually closed source. There are open source HLS tools, but more importantly than that, I think HLS tools are typically in the ordinary way designed as kind of vertically integrated black boxes. That is, these sort of monoliths that take, it's like all the way from a special little subset of C with annotations all the way down to RTL, and there's not like a lot of abstraction layers in between. And breaking up that monolith and doing it, of course, in an open source way is part of what our lab is on a mission to do. So I want to talk about what HLS is good at and why, if you are frustrated with having used HLS in the past, why you might be frustrated. And that is that HLS, that it's the sort of, or the ordinary conception from the programmer's view is that you throw in a C program with like perhaps with a few hints built in, like with a few pragmas you added to unroll loops or to like introduce parallelism or to like manipulate the memories that are generated or something like this. And HLS tries really hard to search for the best possible architecture it can implement, which it's equivalent to the original program, which like, at first, it sounds like a good idea. That is like, why wouldn't we search as hard as we possibly can for the best implementation of the specification? The problem with this is that it is like, I suppose I should like say the positives first. The positive side is this, is it often does find like surprisingly good implementations from kind of vague hardware specifications. But the problem is that when it works well, it's really hard to explain why it worked well, which is what I'm getting at when I talk about predictability. HLS tools are unpredictable in the sense that you give them a high-level description and they work really hard to give you the best possible performance. And there's this sort of fundamental trade-off between things that are more predictable versus having better performance. This is a page from the C2 wiki, the sort of original wiki on the internet, which I sort of found as an interesting rumination on the fact that there is a fundamental tension here. That is, the more you work toward performance, towards sort of performance at all costs, the more you have to sacrifice the predictability of any tool. That is like the ability for humans to kind of understand what the performance of the thing is going to be. You can sacrifice some of that predictability to get kind of optimal performance, but it is a sacrifice. And in fact, like some of the ideas on this wiki page that are kind of fun to ruminate over suggests that sometimes it is worth sacrificing, counterintuitively, worth sacrificing some performance in order to get some predictability, and thereby, in sort of the long term, get higher performance in the end, because the human designers using your tool can more effectively iterate toward a more predictable, a higher performance thing that they're generating. This kind of tension shows up a lot in compilers. Like, for example, if you've ever used OCaml or talked to anyone who uses OCaml, one thing that people who love OCaml love about OCaml is that the language and the compiler have super predictable performance. And I think that was like really well illustrated by this blog post by one of the people who works on OCaml, by Aaron Minsky, who was talking about a new inliner that was being added to the OCaml compiler, just an inliner. But it struck me that that one of the big things that they were worried about, just adding a better inliner with some better heuristics about deciding when to inline, one of the big trade-offs is that sacrifices some predictability. That is, like, just improving inlining does come at a cost in how programmers can reason about performance. So when we started trying to think about predictability in HLS, we had a similar concern, which is if programmers don't understand how code is going to perform or how changes to code will change how the code performs, then it's really, really hard to get a high performance design, no matter how amazing the tool is at like searching very hard for high performance implementations. So I want to convince you that there are predictability problems going on in the traditional way that HLS is done, from C programs with a few annotations. So I'm going to go through a little bit of an example. This example is just a simple matrix multiply going on with just a triply nested loop here. And I'm going to take it through the Vivado HLS commercial HLS tool. So this is the one from Xilinx that targets their FPGAs. So if you feed this program into Vivado HLS, you get really simple hardware and not very good hardware. The arrays map to memories, and then you get a multiplier and then an accumulator. It's not terribly surprising. But if you want to make it go fast, you have to start inserting annotations. So we would, like, for example, like to take this multiplier and parallelize it. That is, let's make 3 multipliers and try to run them in parallel. So the first thing you might try after reading the Vivado HLS manual is to try to put in one of these pragmas, one of these annotations that asks the compiler to give you a higher performing design. That is, to add parallelism in this loop to make multiple copies of whatever logic's inside, run those in parallel, and hopefully we get a faster design. So let's measure that. I'm going to show you this a couple of times, a slide that looks like this a couple of times, rather. And what's going on here is that I'm showing the results of changing one of those parameters along the x-axis here. So this is the unrolling factor. You can put in a different unrolling, like an arbitrary unrolling factor for a loop, and that's supposed to give you sort of more hardware parallelism and make things go faster. And on the 2 y-axes here, I'm showing you the LUTs used on an FPGA when we actually mapped it to a real Xilinx FPGA in the cloud, and the actual running time. So I want to emphasize that these measurements were taken on actual measurements of wall clock time rather than doing any kind of estimation. So it should be the case, hypothetically, that, like, at least from a straightforward understanding, that the more you unroll the loop, the more area it should take. That is, the more multipliers you're generating, but the faster the algorithm becomes. That is, the faster the overall accelerator is. So we should see the left-hand side trending upward and the right-hand side trending downward as we unroll the loop. And of course, that is not anywhere close to what happens. That is, as you vary the unrolling factor, you get essentially no, like a sort of very weakly increasing trend in the area. And you really don't get that much performance. In fact, it's pretty easy to find these red points where you can increase the unrolling factor and actually use more area and also be slower at the same time. So something has gone wrong here. And if you are a hardware expert, perhaps you can already see what it is, but I'm sort of talking from the perspective of someone who is approaching HLS from like an intelligent software designer's perspective. Not that they're stupid, but they don't know too much about the details of like why just parallelizing the multiplies by themselves is not sufficient to get the kind of parallelism that you want. What's going on here is that we have created parallelism in the hardware. The HLS tool has followed our orders and created multiple copies of the multiplier, but it isn't sufficient to get the parallelism we need because we haven't partitioned the memories. That is, there's not enough parallelism to read the data out of the memories on the chip in order to get the parallelism we want. So in order to do that, you need more pragmas, you need more annotations in Vivado HLS, but you can partition the memories to the same factor that you're unrolling the loop, And then hypothetically, you should have enough ports on your memories to read all those values in parallel and to keep all those multipliers going in parallel. So what's sort of going on here from a programmer's perspective is that there's a hidden unwritten rule that creates associations between parts of the program, between annotations like the unrolling factor and other annotations like on the memories that get accessed from the loop, and also the way that you access the memories. That is, there's some sort of a connection here that says that if you obey these unwritten rules about keeping these values the same, then we should be able to give you good performance. But if you stray from those rules, then all bets are off and you might get larger and slower hardware despite your best intent. But it should certainly be the case that if you do obey these rules, you should get better performance, right? Maybe you can see what's coming, but I'm going to show you some more plots here where I've now used the same quantities on the y-axis, but the x-axes are now a different thing. We're not just unrolling the loop alone, we're now unrolling the loop and simultaneously partitioning the memories to the same degree so that we get the amount of parallelism that we need. So it should really now be the case that we get that sort of smooth area performance trade-off that we had before. And kinda, that is, we do get a design that like most of the time goes faster, but the area is actually like quite a bit more unpredictable. That is, like it sort of like bounces all over the place. And it's definitely possible to to unroll your loop more and actually get a slower design. What's going on here is that there are still more hidden connections that the compiler is enforcing for you in its search for the best possible implementation. Is when it tries to obey your program exactly, it is running afoul of another correspondence that you should be aware of, which has to do with the loop bounds. That is, if we unroll with a factor of 3, but we're like running for 512 times, then the entire loop needs extra hardware in order to deal with the sort of uneven division of the unrolling factor into the loop extent. So it needs to have these early exit checks all along the way that cost every single time, that cost area and cost performance. So here's another unwritten rule. You should probably have your unrolling factors divide the bounds of your loop in order to get the best performance. So in order to start addressing these problems, the first project that I wanted to tell you about is a programming language that we designed that tries to restrict HLS to a subset where things are predictable. That is to take those unwritten rules and write them down in a type system that can enforce them for you. So the basic schematic, as opposed to the one that I showed at the very beginning to sort of rag on HLS a bit, is to say that instead of giving a very high level program with just hints to a compiler, we would like to give a sort of intermediate level abstraction to our compiler, run it through a type checker, and as long as it type checks, it should be able to go through a fairly simple, predictable, not very fancy compilation process in order to generate an architecture that the programmer can actually predict. So the type checker is the key thing here. That's the one that enforces the unwritten rules of HLS, that allows the rest of the compilation tool chain to be predictable. As long as you satisfy those rules, then we don't have to do complicated things like automatically inserting early exit checks and loops, and we can sort of more straightforwardly follow the instructions of the programmer, and therefore generate hardware that performs does the predictable thing when you change the parameters. So I want to give you a little taste of this language called Dahlia that we made. This language, that syntax looks a little bit different. It is a different language. It's not just trying to be an overlay on top of C. It has things like being able to declare memories, like this float 10 thing instantiates a memory with 10 elements, 10 float elements. You can do things like read from memories and write to memories, just as you might expect. The important thing, however, is that Dahlia's type system is constantly asking whether it's possible for possibly conflicting things to run in parallel. If you notice, the root of all evil that was in all the unpredictability in the traditional HLS that I just showed you was that accesses to memory were allowed to be concurrent when in fact the hardware can only support a finite number of concurrent memory accesses. So the question that Dahlia asks is it possible for these two things, that is like reading from this memory and writing to this memory, is it possible for those things according to the program to run at the same time? And if so, Dahlia rejects your program and requires you to sequentialize things so that those memory accesses don't conflict. So the particular error that Dahlia gives you, if you try to write this very program that's on the slide, is that the affine resource M1 is already used in this context. So this is getting a little bit into PL nerd land, but Dahlia's type system is something called an affine type system. Affine type systems are related to linear type systems, which are part of a broader family called substructural type systems. And I promise to stop saying adjectives in front of type systems very, very soon. But these substructural type systems are what underlie things like Rust, if you've used Rust, that try to track things as resources throughout your program. In Rust, those resources are memory allocations. That is what Rust is trying to do, is make sure that you keep track of memory allocations so it knows exactly when to free everything when it goes out of scope, for example. What we're doing in Dahlia is somewhat similar. That is, we're tracking resources as they flow through programs, but those resources are physical hardware structures, in particular, memories. That is, we deal with M1 here is an affine resource in the sense that it can be used up and then not available again in the future. So the way this type system works is that it says when you do M10, when you read a value from M1, that uses up the resource and it's not available to the rest of the program, which is because of a very funky thing about the semicolon in Dahlia. That is, Dahlia, in most programming languages you're familiar with, what semicolon means is sequential composition. That is like, do this thing, and then after that's done, do this other thing. In Dahlia, it means something else. It means in particular that we allow the things on either side of the semicolon to run in parallel, to be parallelized up to the data flow limit. And by that, I mean that this is what's traditionally going on in HLS compilers. That is, it's looking at your program and every statement is potentially allowed to run in parallel. So this semicolon is called unordered composition in Dahlia. And what it means is that, because everything is allowed to run in parallel across semicolons, when you use up hardware resources, those remain unavailable to other things that also might run concurrently after the semicolon. Dahlia needs a way to work around this. So Dahlia also has a different form of composition here written with the very the imposing syntax, a triple dash, to say to give a visual indication of a kind of time step that is saying that like first we're going to do this and then later we'll do this. That's called order composition, and it means that the thing actually runs sequentially. That is, like, it's no possibility for these things to run in parallel. So Dahlia likes this program. It says that because you have done the hard work of proving to me that the use of M1 for a read and then for a write are ordered in time, I can accept this. According to our affine type system, this is safe in the sense that I know how to implement it in a predictable way.
So yes, so we didn't mention before, do you want questions in the middle or questions at the end? Or
totally happy to take questions in the middle. Sounds good. Yeah.
So just curious, if you have like an expression to access the memory, the problem is that it might not be clear if they overlap or not. Mm-hmm. How do you handle those cases if I have an expression that it depends on some inputs and you don't know? It's like if it has some may alias concept.
Great. Yes, we sidestep that issue entirely because there is no aliasing in Dahlia. So it's impossible for the same memory to be given two different names. That is, like, you can't call the same memory M1 and M2. Of course, there's aliasing at the level of elements instead of memories.
Yes.
And that is handled completely conservatively, in the sense that we're not just saying that you need to have exclusive access to individual elements, but entire memories. So even though M1 and M10 and M11 are different locations, they're still illegal to access concurrently because of the ports on the memory, not because of the values inside the memory. Does that make sense?
So here is M0 and M1, even though there are different locations, even there were different banks, there will still be a conflict. Or how can you guarantee that it goes to a different banks?
Great question. Banks will come up in just a second. So far, let's just assume that this is a single bank, and that's why it's illegal to access even two different locations in the same memory. Cool. So let's talk about banks. So the basic idea here is that Dahlia has for loops, for loop construct with an explicit unroll annotation, which is does recall exactly what's going on in HLS. The only thing is that its type system, it also has a bank annotation on memory. So when you declare a memory, you can say how many banks it has. The difference is that something more nuanced is going on with the way that we type check for loops. And that in particular is that we need to enforce that whenever we access a memory, we know that there are sufficient banks available according to the current context in the for loop to allow that for loop to like sort of run at full speed. That is the parallelism, the degrees of parallelism match. So the way that it does this is by imbuing the type of the loop iterator with a special type. So in Dahlia, like in a normal programming language, I here would be of type int. That it would just be sort of a normal integer loop iterator. What goes on in Dahlia is that I is a special type of a loop iterator that carries around the information that it is, it's not just access, when you use it to access a memory, you're not just accessing one bank, you're actually accessing 3 banks in parallel. So when you, to type check the like M2I and M1I subscripts, you have to sort of you need to prove that the amount of parallelism demanded by I, that is demanded by the loop whose iteration variable is I, is available in those 2 memories. So I hope that answers your question about how.
Yeah.
How this
so you have to understand. So for example, in the line that you have M2I, if I put I plus X and I put plus X in both of them, in theory, it will not overlap in banks, but you don't allow that, no? It has to come from the range operator.
Indeed, yes, right. So things get a little bit more complicated in this, and I think I have a slide on this next to do like actual index math. But I guess like in the most basic version of Dahlia, you can't safely do accesses like with arbitrary index math inside these brackets. That is, you can just use I because that's what we can prove has sort of non-conflicting parallelism. As soon as you start wanting to do like plus X, for example, inside here, we need to know something about X in order to show that that access is still safe. And that is the job of the next construct that I apparently do not have a slide about. But I guess the point is that like this basic version is enough to prove that like really simple iteration patterns are safe. And then we need a way to prove that like more complex ones that, for example, like go over a single bank or like use an offset within an iteration. Like we need a way to prove that like those things are also safe. And the way that a traditional HLS compiler works is it lets you write, just because it's just C, you can write like arbitrary expressions inside the square brackets next to M2 and M1. And it just kind of like does its best to try to make that safe. Our thing is sort of, we use a series of combinators called memory views that let you sort of adapt the access pattern in a way that is still provably safe. That lets you, for example, apply offsets or to like iterate over a subset of the array or to combine them in interesting ways to get combinations of those effects, while still all along the way doing this kind of typey proof that you are iterating with the correct amount of parallelism.
So kind of going off that, I think maybe I can almost predict the answer is going to be, since you said you can't have super complicated indexing, does that mean you can't do indirection, like a data dependent address?
Oh yeah, that's total anathema to this approach for sure. Yes,
Okay.
Absolutely. Yeah. So like doing things with like indirect access, of course, super important. You can write them in Dahlia, but you can't parallelize them because we can't prove that they are safely parallelizable. Does that make sense?
Oh, definitely. Okay, yeah, there's a lot to think about for graph stuff. So I'm always worried about how to handle indirection and what a pain in the butt it is. Okay, great.
Totally. Yeah, I think sort of taking this into a world with like trying to do more complicated dynamic parallelism stuff, like where where indices are more loop dependent, more data dependent and stuff, I think would be a cool like different take on this, but it's not something that Dahlia itself covers.
Yeah, this is great. This is still really helpful to get this problem started.
Sweet, cool. All right, I'm going to show you a few results where the main question that we were trying to ask with Dahlia was like 4 things that fit into its domain with its like fairly regular kind of statically predictable parallelism stuff. Is it too restrictive? That is, like, even in that domain, does it overly restrict programs so that it's no longer possible to write high performing implementations with like using an HLSD style? So the problem you can imagine is that like it's just like we are restricting the design space down so far that there's like lots of HLS programs that you can write, and a lot of them perform actually better than the ones that Dahlia can certify as being safe. That would be a problem, and we want to make sure that was not true. So for this experiment, what we did was we took a little a blocked matrix multiply. So it's just slightly more complicated than the naive matrix multiply you saw before. And what we did is we took it and did a very large design space exploration of 32,000 points. And ran it through Vivado HLS's estimation mode. It took long enough. It took like, what, 2 or 3 compute months on EC2 instances to like just do the estimation on this. And then we sort of like plotted this Pareto frontier. So this graph is showing like every single point is a different design point on the, we're fiddling different like unrolling factors and partitioning factors on memories and stuff like that. Every point is plotted on the x-axis for its latency, that is performance, and then on the y-axis, the LUTs, that is the area on the FPGA. I'm highlighting in purple, those are Pareto optimal, or purple and green, those are Pareto optimal in the entire large design space. And you might notice that the purple points don't really look like a Pareto frontier on this plot, and that's because they're Pareto optimal with respect to all the FPGA resources, like including DSPs and block RAMs and stuff. Not just the LUTs and latency that are plotted here. What the green ones, that is 15 out of the 56 Pareto optimal configurations, are also accepted by Dahlia's type system. That is, if you take those annotations and you write that thing in Dahlia and then you type check it, then these ones are certified as type safe by Dahlia. So Dahlia certifies 354 out of the very large space, out of the 32,000 points. And out of those, 15 of the 56 Pareto optimal ones are accepted by Dahlia. And qualitatively, it does mean that we missed some things that are in the Pareto frontier, but qualitatively, we do get like sort of a nice like wide range of the Pareto frontier, meaning that like if you wanted to do a design space exploration aided by Dahlia and you just explored the 354 points, you wouldn't get a bad range of possible designs. You would get one that spans the range of good designs. And most of the ones that we missed, and again, this is qualitative, are ones that made like kind of questionable trade-offs, like spending a lot more LUTs to get a tiny bit more performance. That it's up to you to decide whether that is a worthy design point to explore. But overall, we are happy with this in the sense that if you use Dahlia's type system to restrict your design space to a much smaller set, then you can do that DSE a lot faster, and you don't lose out a lot on the overall performance of your design. This was published at PLDI this year. The Dahlia paper is called Predictable Accelerator Design with Time-Sensitive Affine Types, and I encourage you to check it out. You can also go to the website that hosts some more information about Dahlia. One really cool thing that Richard Nigham, the PhD student who led the Dahlia design and implementation, did is make a little embeddable widget on this page where you can write Dahlia programs and type check them and get all the type errors you ever wanted right in your web browser without having to install anything. I think now would be a great time to pause and answer questions about Dahlia, if anyone has any questions before I move on to something else.
So yes, quick question. I think it's different, but I see do you know the Google, the XLS project that it was released recently? So what is your take on that one? Because it's also trying to do XLS a little bit high level. I'm not so sure if they have loops, but I don't know if they have the unroll constructs. I don't think they have any of those conflicts on memories. But
okay. With the caveat that I don't know terribly much about what's going on in XLS. I know the high order bits from chatting with them a tiny bit. But the really cool part about it is that we are very much on the same page of like, let's do something like HLS in the sense that we want like higher level languages for designing hardware, but also not like HLS in the way that like their philosophy is very much don't hide things from the programmer. That is, like programmers are smart enough that they can reason about this stuff. So from that perspective, we're very much on the same page. I mean, it goes without saying, but like this like affine tracking stuff is unique to Dahlia, and it would be super cool to see that applied to other languages like XLS and their entire compiler framework. I think that'd be super cool.
Okay. If there is any question from the audience, we can promote you. You can raise your hand, or you can put it on the questions on the panel, and we can bring the question to the speaker if you want. If not, maybe you can continue, and
Cool, great.
I'll have more
Awesome.
questions.
Great, cool. Okay, so I wanted to talk a little bit about a second project that was inspired as kind of by implementing the compiler for Dahlia and writing programs for it. In particular, we got it into our heads that we should sort of like, in the way that Dahlia that the original compiler for Dahlia worked was that you type checked Dahlia programs and then you translated them to a heavily annotated C++ that you could then feed into Vivado HLS. So we were still stuck with an actual HLS tool. We were able to make it more predictable by restricting the set of programs that you can express, but we're still just using an HLS tool in the backend. And this felt like a sort of a great shame to us. And instead, it sort of struck us that like when you do traditional HLS, when you sort of start with a high-level language, it's weird to call C a high-level language, but it absolutely is when you're generating hardware. Is the HLS tools have a lot to do. That is, they're amazing feats of engineering that like do a lot of work in order to guess what you want from the program. So like this is again what makes them amazing, what also makes them frustrating is that they're so complicated. These vertically integrated things that like work very, very hard to sort of guess what you want and to give you the best possible hardware that does what you want. It occurred to us that like with Dahlia's philosophy, that is like with being a lot more restricted and being a lot more tied to what hardware can actually do, that is hiding a lot less from the programmer, we thought like, well, the compiler itself can be a lot simpler. That is like, there's still stuff that we need to do. That is, we're not going to get away from like doing kind of doing scheduling at the level of individual operations and stuff, but there's like stuff you don't have to do, like trying to figure out how to automatically come up with banking policies, for example. It's not something that Dahlia needs to do because that's sort of encoded right in the program. It's something we've factored off from the compiler and given back to the programmer to be in control of and to worry about. So it should, like, you know, by all rights, be super easy to write a compiler for Dahlia that generates RTL, right? This, of course, was our folly. We thought it would be like not terribly hard to go from a restrictive language like Dahlia and to do something like HLS, but much simpler for its semantics. And so that's how we got into this business of trying to build a compiler infrastructure for languages like Dahlia that want to compile to RTL, in particular, for our purposes, primarily to FPGAs. And so there's an analogy here, which I realize is claiming a lot, but like there's something to this. And I don't want to say that this project is going to be the next LLVM, but we're trying to learn some lessons from LLVM. That is, in particular, LLVM has a lot to offer as a compiler infrastructure for targeting CPUs. And we think that there is room for compiler infrastructures, language agnostic compiler infrastructures that are for generating RTL, that is for generating hardware designs that then need to be compiled the rest of the way to reconfigurable hardware. And the philosophy that they share, this project, which is sometimes called futile to sort of poke fun at it being slightly overly ambitious, is to replicate LLVM's philosophy to break up the monolith. That is, instead of having a big vertically integrated ball of wax that does one thing pretty well, let's try to decompose it as much as possible into small modular layers. So I'll show you what that looks like. So the futile stack, like the hope is that we can compose an entire compiler for a high-level language out of a lot of individual small passes instead of like one giant ball of wax that all operate on an intelligible and self-contained intermediate language. So the intermediate language is key, just like it is in LLVM, that it has an independent semantics that aren't tied to C and aren't tied to RTL, that is possible to reason about independently and to do optimizations on the way from a bunch of possible high-level languages to a bunch of targets. That is, for let's say for the world's FPGAs and maybe future CG arrays beyond that. So the trick with doing this is that we need a representation for programs that allows us to do HLS-style optimizations. And so this slide is meant to convince you that, that existing intermediate languages are not the right fit for this level of optimization. So the two categories that you might imagine are existing intermediate languages that are meant for software, like LLVM, for example, or existing intermediate languages that are meant for hardware. So that includes, for example, the LNAS project from Santa Cruz. these things are like, of course, we need to sit on top of lower level representations for actual RTL, like LNAST or Fertile or something. But the optimizations we're talking about are at a higher level. And the key thing that we need is a way to represent both software semantics and also hardware resource allocation. So doing things like generating a finite state machine to implement some control flow through a program, we want to implement that as an optimization that stays in futile land. That is, that goes from futile to futile in a different form. So like that sort of an implementation, the lowering pass or an optimization pass requires that the representation be able to represent kind of control flow and software-like semantics, but at the same time, be able to represent the sort of structural design of hardware components. So if the kind of philosophy that futile takes is to blend what it needs from these two different representations. So on the left-hand side, we have this is LVM, and the way that LVM and like any representation, any like sort of IR for software works is that it's purely about the control of the program. That is, it has branches, for example, to dictate like what's going to happen first and what happens next. And it's all about the operations that happen over time. So for example, if you wanted to do a sort of, if you wanted to implement a optimization pass whose job was to do resource sharing, in the sense that you wanted to take two different additions that happen separated over time, and you wanted to collapse them into a single adder in hardware, a software-like representation like LVM doesn't cut it, because there's no way to say that these two adds that happen at different times in the program, that those two adds need to map to the same physical hardware adder. On the other hand, if we imagine doing the same thing with RTL, here's like some cartoony Verilog or whatever, to say that like, yeah, we got a couple of modules that both use adders, for instance, and we want to optimize this. The thing about the problem with doing this on an RTL representation is that there is no control. That is, like this more structural representation doesn't tell you the sequencing over time of the operations. That has to be encoded already in some sort of a hardware component, like a finite state machine, that dictates when these modules run. So if you wanted to determine that like these two pluses in your Verilog could actually map to the same hardware resource because they're used in kind of a mutually exclusive way, this would require somehow sort of reverse engineering the execution schedule back out of the RTL in order to understand that they're separated in time. So the idea in futile is basically to smash together these two aspects. That is, to have both an explicit representation of control that we can analyze to get to like understand what the accelerator is doing over time, and then also to have a structural element so we can talk about actual hardware resources. So I'm gonna give you a tiny introduction to what the intermediate language looks like. You can instantiate components just like in any old RTL language. Like for example, you can make a register. But the way that they start to diverge is that you can group those things and their connections into these things called groups, these named groups. So this connection between a constant and a register, we can wrap up and say that's called init. And the reason for doing this, but here's a different group that has like sort of an overlapping set of components and other connections going on. The reason for giving names to these groups is so that we can address them in the control part of the futile representation. So everything that's the instantiation of these components and then the groups with their connections, those are all pretty reminiscent of what goes on in an RTL representation, that is in some sort of HDL. The control bit, that's different from RTL. This like control thing says, here's what happens over time. And there's sort of a library of control operators, the most basic of which is seek for sequential composition, that says, here's what you're going to do, architecture. You're going to run the init group and then run the update group. That is like to sort of, you can sort of imagine like the entire design being like powered off. And then magically from outside the hardware, someone comes along and says, okay, init group, you now go. And then you go in the update group. So this looks like an ordinary imperative programming language, but the primitives in the imperative language reach into the structure of the design and tell you like which parts of the design to go at a given time. This means if we want to do something like that register sharing optimization, we have the information that we need. So for example, here's a slightly more complicated version of the program that has like a couple of a couple of copies of the code you saw on the previous slide. What you would need to do is identify parts of the code that can't overlap. That is like sort of analyze and look for sequential composition, which means that these groups can't run at the same time. And then look for primitives within them, that is combinational primitives that are identical, but use different primitives. That is like these two different adders. And then we just have to rename this adder to a different one. So in this representation, we have all the information that we need in order to represent this as a kind of self-loop pass on the same intermediate language. That is, we have the control information that we need to analyze to prove that it's safe, that we can do this resource sharing thing. And we have the structural information to represent the results of this optimization. That is to say, we no longer have two adders, we only have one, and we're going to use just that one adder and then nominally, I guess, reduce the area of our design. So the way that the Futile compiler works, Futile is implemented in Rust. So it has it's not just the language, but also kind of the accompanying infrastructure. By that we mean like a series of existing passes and a backend that generates Verilog. The way that it works is that it has sort of this series of lowering passes where a high-level language, like for example, Dahlia, can generate a program that has a whole bunch of control, that has like a bunch of seeks and pars. It also has I didn't even mention par. Par is explicit parallelism that's represented in the control program. It also has things like conditions. It has if and while, like normal stuff from imperative programming. So Dahlia generates Futile programs with a whole bunch of that stuff, and then it feeds into the Futile infrastructure that bit by bit, pass by pass, transforms that control stuff into a purely structural representation. And by the time that Futile doesn't have any control left and is just made of groups, that is just components and their connections and stuff, then everything is active at the same time. And that is pretty much isomorphic to RTL. So lowering from that into system Verilog is what we output, is pretty straightforward at the end. That is the high level that without a lot of optimizations performed, the high level version of Futile is pretty far from RTL, and the low level version is pretty close to RTL, which means it can be translated out of it. I see we have a question in the Q&A thing here, which asks, can Futile generate chisel or pymetal? Futile is targeting Futile targeting Verilog? Yes, Futile is targeting Verilog for now. We think it would be super cool to generate a one of the many very solid seeming intermediate languages for RTL. It was just a little bit easier to just glue together Verilog ASTs when we were prototyping this. We think it would be very cool to build more backends. This question in particular is do we generate chisel or pymetal? And an answer to that is a slightly more emphatic no, because we're not trying to generate source code. That is, the fact that we generate Verilog is just out of convenience. At the moment, we're not putting any effort. And in fact, I think it would be pretty hard to generate Verilog that humans actually want to read. The Verilog that comes out of Futile is extremely miserable to look at. And so generating something like chisel or pymetal, I don't know if it would have much of a benefit. Of course, you can imagine hooking it into larger chisel or pymetal designs, and that would be cool. Pymetal, for example, has a bunch of cool testing infrastructure. It'd be good to take advantage of, but generating actual Python source code, I don't think that would be terribly useful for Futile. I hope that answers your question. Cool. Okay, so the next thing that I want to do is to take the rest of the time to give you a tiny demo of what this infrastructure looks like. But now would also be a great time to take questions if folks have further questions about the kind of overall Futile pitch. This slide, by the way, you were not meant to read. This one's for me in order to remember what to type for this demo.
So it's very interesting. It's we are working on the LifeSA project. So yeah, we totally have also the intermediate representation, but we have a very different approach. So in our case, we have two level representations. Mm-hmm. So one is the LNAST, which is more like a tree-like control flow AST structure. So the name is for language neutral AST. So it gives you a good hint. And then the other one is a pure data flow. That is what we do is we translate. It's more like from a compiler point of view, it's a gated SSA. It's not a normal SSA, it's more a gated SSA. And it's pure data flow, but it has hierarchy. So it's a graph representation with hierarchy, and we have a lot of support to traverse those hierarchies. Now, one thing that I don't know how you generate is that you have those groups, and I can see how they work, but to translate from some language to those groups might be a little bit challenging. Like, for example, if I were getting some Verilog and I wanted to translate to those group functionality, I'm not so sure how will I do that.
Oh yeah, totally. Just to be clear, I don't know how to do that either. That is like going from from normal RTL into futile is kind of the opposite direction of what we want to do. That is like where like this is the stack is kind of for getting from much higher level representations to RTL. That is like eventually we eliminate all the groups and we have like a purely flat representation that is easy to translate into Verilog. But going from Verilog into futile to do more stuff is not really a goal. And I totally agree. It would be pretty hard. That is like to sort of divide stuff up into these kind of atomic action type of stuff.
Okay, so I guess that's another difference for NordFlows, because in our case, it has to accept full Verilog, anything synthesizable in Verilog.
Absolutely, yeah.
And that's a lot of things like asynchronous latches. I had to support all that junk.
Exactly, yeah, right. So that is like, in a way, it's very freeing for us that we're not actually trying to do that like very important and very ambitious thing to like make a tool for like transforming like, you know, your favorite RISC-V CPU, for example, is not really a goal for us. Instead, we're doing this in some ways more exotic thing. We're trying to support like compilers for high-level languages to like make your tensor compiler or something like that.
Okay.
Cool. Okay, so I'm going to give you just a tiny demo of what's going on here. So I have like pre-prepared this like very small Dahlia program. Dahlia used to be called Fuse. That's why the extension is this. Anyway, so this does a really dumb thing. It's got a memory and it just like adds two numbers together and then puts it in the output. So I want to show you what it looks like to go from this to futile. So that's, wait, I forgot that this, this didn't work anymore. I think I just need to do tiny futile. Great. Okay. So this is the result of doing sort of a straightforward compilation of what went on in the original Dahlia program. So we have. I'm going to dive a little bit into the code here, so please forgive me. You don't need to like read everything that's going on here. But what's going on in this futile representation is that there's sort of a list of cells. Like for example, this std-mem, et cetera. That's a memory. Then of course there's a register, and then there's like these constants and stuff here, and then these groups kind of like organize that. And the three groups that the Dahlia compiler generated are one to read from A, one to read from B here, and then one finally to write the result of the add to C, that is like to put the output into C. And then somewhere in here is an adder. We can have a good time trying to find this. So add 0, it's called. Does anyone see it? Okay, yeah, down. Okay, so it's in this one. So this sort of like takes the results of the two read stem memories, does the add, and puts it into the result in C. So the control part is also pretty simple for this, which is that we're going to, the overall thing is sequential. That is, we're going to do one thing and then another thing. The thing we do first is to, in parallel, read from the two arrays. And then after that, we can do the add and put it into the output. So this is what the Dahlia front end has to generate. That is like, it sort of has this sort of like small toolbox of sort of sequential and parallel composition and if and while and stuff that it can use to implement statements that look like this in the original code. And then it can generate, it can generate like a code that's like pretty isomorphic to that in the control section that uses resources allocated there. So if I were to do pass all on this, oh man, oh right, okay, I forgot I have to invoke something else. Okay, target. So this is the same thing, just nicely syntax hided. Okay, great. But if I'd say pass all, then this will run the full stack of optimizations and lowering passes on this. So we're going to go from this nice, almost readable futile program that, like, with 3 different groups and this seek and par and stuff going on, we're going to, this will, I hope, eliminate all the control and ruthlessly flatten all the groups. So we have a fairly illegible, but fairly close to RTL futile program that we can then emit. So I'm going to try doing that now. Great, it seems to work. Fantastic. Okay, so this is no fun to read, but like this has eliminated all the groups, and you can notice that now the control is gone. That is, we've done all the lowering that has gotten rid of the high-level software-like semantics. So I think now if I do b verilog, like this just has to do a really simple translation to, again, really inconvenient to read terrible Verilog that implements the same semantics. That is, like, once you're in the very low level form of futile, there's not much to be done in order to get the rest of the way. Okay, so now I'm going to try the part that is the most likely to fail. So please bear with me. Actually, I'll show you this example. This is like only like marginally more interesting. It like just puts a loop around that around an addition, but we're just like adding together 2 vectors. If we do this, I hope that this should generate Verilog in sort of one fell swoop from that. Okay, great. It's like long and unreadable and terrible, but we can also execute this. So if I add a couple of incantations here. This should, I hope, just like actually run it. But that means that it's compiling it to Verilog and then running that through Verilator in order to go to like actually run the thing and then give me the results. That is the stuff that's in the output array. So hopefully this is the contents of one of the input arrays. That's the contents of another one, and this is the contents of the sum. And that looks right to me. It looks like it added all that stuff. So I think we're in business. Okay, so anyway, that's a little bit of the tooling that's around futile, just to sort of show off that you can actually use Dahlia compiling without Vivado HLS at all, going through the futile chain and executing in Verilator. I don't imagine that there are any questions raised by my my command line invocations here, but does anyone have any?
No, that's good. The only thing, you didn't show the example that drives the test?
Sorry, the example that writes the test?
No, that drives the input. So you put 2 files here, the views and okay, the data, you are reading it from that. Okay,
yeah, this is just a JSON document with the original data. That is like it has those 2 input arrays and then zeros in the output array. Yep. So it's just the cool data for the memories. Yeah. Cool. Alrighty. So basically, to wrap up, like this is actually, I don't have too much to say about this. This is just a diagram of what's going on with futile. We do have a Dahlia compiler. It goes through all these passes. It's pretty cool. We also have a just to sort of demonstrate the breadth of what's going of what futile is capable of with something that looks as different as possible from Dahlia, which is a systolic array generator. That's the cartoon on the bottom there. We're also working on trying to get a kind of a more interesting case study going by compiling TVM's IR called Relay to generate implementations of neural networks as a way to sort of exercise futile on larger programs. So you can totally check out futile if you like. It is on our GitHub page, and you can learn those those elaborate command line invocations I was just showing you. To if you want to, you can compile Dahlia programs to your heart's content and run them through Verilator. That's pretty much all I have. I wanted to emphasize that all the stuff that I'm taking credit for today was actually done by a talented group of grad students and other students in our lab. Some of them you see on the slide here. There's even more involved than I could fit just with the names on the bottom. Anyway, this is a pretty big project, and people have done like truly amazing work. So I wanted to give as much as possible credit to them. And if you want to read more, you can check out our group website here on the slide. thanks everybody.
So thank you very much. Let's see, there are some other questions from attendees. If not, well, maybe they are thinking. So there is a Cornell, there is the PyMetal, there is the Dahlia. There is also some other work with HLS there. Do you see using the Futal as a way to interface with PyMetal, or the issue the PyMetal goes a little bit lower level, so it's not clear how to interface it? But I'm sure that you have been thinking about that.
Yes. Yeah. Okay. So here's what I keep on talking to the folks who work on Futile. I'm sorry, on PyMetal about that I think would be cool, is trying to answer the question, like if you're trying to do a big or even medium-sized accelerator design, is there a useful way to kind of like gradually transition from higher level generation that is like sort of DSL style or Dahlia style design down to my cat just broke in. Okay, great. To sort of like to smoothly transition down to RTL design? Like, is there a reasonable division of labor where like some stuff you want to do in RTL and some things you want to do at a higher level representation? Lefty. And it doesn't make sense to have like a single framework where you can like generate some parts of your design more quickly if they don't matter, or and then like switch over to RTL for like kind of fine tuning on other parts. I think that's a super interesting open question. If anyone has any thoughts, I would love to connect offline about sort of like smoothly transitioning between HLS style and RTL style design in the context of a single accelerator. And that's like something I would love to do by interoperating with something like PyMetal.
Okay. Yeah, it's a lot of work there. But it's very nice. We are working on similar, somewhat related, not so much HLS, but it's somewhat related thing. So clearly, we like this type of work.
Cool. Yeah.
Yes. So dovetailing in that last comment, that's really interesting. From far away, for me, the amazing part about PyMetal has always been exactly that. It's kind of mixed model kind of simulations. I think it's been its greatest strength. And so I guess one thing I've been kind of pondering about is, kind of appreciating how HLS fits into the big picture, where, for my background, of course, I'm, partial to Chisel, but, it's clear it's not the answer to everything, right? And, for example, as Jose mentioned, XLS from Google seems very impressive as a new HLS kind of like thing. And, going forward, I kind of imagine maybe there's room for both, right? There's room for like a HLS kind of tier of language and a, efficiency level language, kind of like how in software we have, more productive languages versus more efficient languages, right? And so for me, kind of the big dividing line has been between the HLS versus the efficiency languages has always kind of been the notion of who's control over timing, right? Where in RTL, you're usually describing things in a cycle accurate manner versus HLS, you're kind of saying, get this done. I don't care how or when you do it, right? But as you kind of mentioned in your talk, there's like a zillion things, right? There's parallelism, there's blocking, there's, all these things. So it seems like, I guess, Dahlia right now is most concerned about just flat out safety, right? Is this allowed to be concurrent with this other thing? But is your roadmap going forward worrying more about optimizing or how to we can identify opportunities for blocking or identify opportunities for other things? Because you kind of mentioned, hardware reuse, which is a great thing with Futile, but I mean, is that maybe a direction you're heading or?
Yeah, it's a super good question. And I think that the question of not just timing, but like parallelism in general, like who's in charge of that? Is it the programmer? Is it the compiler? And if so, like which level of the compiler stack, I think is a difficult question that is maybe difficult because it has so many possible answers for different scenarios. That is like, of course, if you're designing a branch predictor, I think it makes a tremendous amount of sense for you to be in charge of the timing. Like you should like sort of that like RTL seems like exactly the right thing. But beyond that, for like doing kind of like garden variety accelerator design, it seems like many possible answers to this are viable. That is, like sometimes you want to be like in charge of individual cycles. Sometimes you just want to say like these things are parallel and these things are sequential, and that makes more sense. I think almost never, however, do you want to leave all of the timing and all of the parallelism up to the compiler. That seems kind of like a losing proposition, and is maybe why people don't like HLS, is because you have like little to no control over the timing at all. So one of the things that we like about Dahlia is it's kind of one of these intermediate points. It's not the only intermediate point, but it has kind of logical time going through it. That is, like you can say this happens after this, but you're not manually allocating things to individual cycles. that's left to the compiler. That strikes us as like a pretty good division of labor for at least one level of abstraction. One thing that I would love to explore in the future that I hope Futile gives us the foundation to do is different levels of automation. That is like different levels of like letting people specify things at different levels of specificity in the like going from all the way from coarse grained logical time down to physical time, and then letting the compiler fill in the gaps when you don't care to specify.
Now, one thing that I didn't expect is like when you are running the simulation, you are running the simulations in Verilog. So you generate the Verilog and you run Verilog. Yeah. But if you do that, you are going to lose a lot of speed in the sense that you are creating a very much slower flow. You have the for loops in Dahlia. You don't need to do any unrolling. You can just use that more high level construct, not to have so much timing exact model that Verilog gives you, and it should be much faster simulation. So why are you not doing that?
Great question. The answer is that the first backend we had to build was one that would let us run on real FPGAs, and that meant generating Verilog. So running things through Verilator is kind of sort of a nice consequence of that. We are right now, the student in our group is building an interpreter for Futile that is meant to be is meant to do exactly what you said, which is to like not be crazily optimized, but be a good reference for the semantics, and also to be more efficient than generating Verilog, because we in cases where you don't need a VCD or something.
Okay, but it's an interpreter. It's not a ahead of time compilation. Or are you doing the LLVM JIT, or that's the interpreter for you?
Right now, we're pretty happy with just starting to do an interpreter. Like I think it'd be super cool to do a JIT when like actual performance becomes an issue. But part of the goal for us, to be perfectly frank, is just to have a better reference for the semantics of the language, for which an interpreter is exactly the right thing. That is to have like a sort of a slow sort of known good reference for what programs are supposed to do, and then we can compare it, for example, against the generated Verilog or against this sort of imaginary future JIT to make things go super fast. That'd be cool.
Now, another very low level question, because we are fighting now with sign and sign kind of thing. So how do you have the internal representation? You have types, sign and unsigned, and then you have to deal with mixing types, or do you have everything unsigned, or how do you do those things there in Futile?
You're gonna hate this answer, but Futile's representation. So Dahlia, of course, because it's all about type systems, has a pretty complicated type system with like it's got fixed point and floating point and integers and stuff. But Futile has the world's dumbest type system with respect to values, which is that everything is just an n-bit signal. That is, we don't know what's an integer, we don't know what's a fixed point. That's entirely up to the front end to enforce consistency at that level. And everything is just, I mean, you can think of it as unsigned integer, but it's just a bundle of bits.
But then when you do copy propagation and things like that, the operation, everything is unsigned for when you do value propagation and things like that.
Yeah, that's right. Yeah, everything is just sort of like a pattern of bits. We have been talking recently about what it would look like to design a type system that can like actually enforce properties like, if you add together two things, then you're not adding an int to a float, for instance, which would be very cool, but we have not done it yet.
And I see there is a question there. I think you can read them, no?
Oh yeah, so this question asks, how do we know that the Verilog is correct? Which is a great question. We know it's correct because we don't know that it's correct, to be honest. And like, because Futile is a pretty young project, it is often incorrect as we are working on it. The way that we assure correctness, the main tool that we have is differential testing. Differential testing is a fancy phrase that just means you have two different implementations of the same language. You can run them both and then check that they are the same. So we have the old compiler for Dahlia that generates C++. We can just compile that C++ with like GCC or whatever and compare the results. And that's how we know we're getting the like, hopefully Futile is behaving correctly. This is absolutely not what you asked at all, but one avenue that I would love to explore, like someday much farther down the line, is formal verification of the compiler stack. That is something that seems pretty hard to do for like normal HLS because the compilers are so complicated. May actually be feasible in something like Futile because the individual passes are sort of small and modular and can be verified independently. And we have an actual semantics for the intermediate language.
One interesting point you mentioned in your talk was you were less worried about taking, like risk processors and more worried about, helping be a backend for some high level application kind of, generation flow. That's really interesting. Do you find there's anything that those kinds of scenarios require some sort of constructs or usages that perhaps those tools find really helpful, but humans never think to do themselves?
So I guess I lost a little bit about what these tools are. So I got your high level point.
So I'm imagining something like TVM, right? So TVM, make a backend for TVM that talks to Dahlia and Feudal, right? So the person who's making the interface between those two frameworks, is kind of connecting these various, constructs and IRs. Did they find there's something that makes a lot of sense for that kind of bridging? That perhaps if I was a human writing, a language by myself as, random IP, I would not ever think to use.
I see what you're saying. Yeah, I mean, so the big one is that, like, for example, when you're compiling Relay or whatever to Futel, you make really heavy use of that imperative control language. That is, like, you're sort of constantly saying, like, sequentially do this thing and this thing, and in fact wrap that whole sequence in a while loop that checks a condition, and like that kind of thing is like incredibly helpful when you're translating from a higher level language that also has while loops and also has like sequential composition of statements and stuff, and like is a reading and writing from memories. And is the kind of thing that, like, if you're designing actual hardware like from scratch, like in Chisel or something, that's not the way that you think. Like you're not like writing while loops that are like to sort of like implement the control of your processor. But it's like when you're implementing higher level languages, that's exactly what we think you need.
Cool. Well, that's really interesting.
So any other question? Otherwise, we have been a little bit over an hour, but I really enjoy, so it's okay.
Maybe we can thank our speaker one more time.
Thank you, the speaker virtually. So thank you for coming to give the talk. Very interesting work.
Had a wonderful time. Thank you so much for the invitation, and I will talk about this all day if asked to. So thanks.
Yeah, thanks for coming.
Great. Talk to you all later.
See you.